In this section, we will talk about forward error correction coding. In particular, we will talk about convolutional encoder and a Viterbi decoder. Convolutional encoder is used both in 802.11a for Wi-Fi and also in 802.16-2004 for WiMAX. This section covers material common to both Wi-Fi and WiMAX. Forward error correction is essential to achieving robust and reliable communications over wireless multipath fading channels. Here we show the block diagram of the OFDM transmitter, and at the bottom the OFDM receiver as implemented in 802.11a. We're showing a number of blocks that you may have not encountered before, but are important in terms of setting the context for the correct operation of a forward error correcting code used in a wireless multipath fading channel. Here we show the data which is scrambled and randomized, and we have the convolutional encoder. The convolutional encoder essentially takes the incoming data bits and adds redundancy. We take the initial information bits, add redundancy, transmit it through the channel adds errors, and the decoding process uses the redundancy in order to correct for those errors. Typically in a wireless digital communication link in which you have fading multipath channels where you can encounter deep fades and a carrier, for example, could be wiped out, it is not sufficient to add a forward error correcting. The problem occurs as follows. If during the transmission a particular carrier is wiped out or happens to fall on a deep fade, then all the encoded bits associated with that carrier are an error, and you have what you call a bursty error. Many forward error correcting codes are not good at correcting bursty errors. That is, errors that are associated with bits that are adjacent with each other. Many forward error correcting coding methods actually correct random bit errors. In this case, for convolution encoders and using the Viterbi decoder, it is very powerful in correcting random bit errors within a block of bits. The nature of a fading multipath channel is such that multiple carriers can be eliminated or are received with a low SNR, causing bit errors that are bursty in nature, and this forward error correcting coding technique will not work very well. This is why I am showing the inclusion of an interleaver block at the transmitter and a de-interleaver block at the receiver. The interleaver takes the incoming bits and permutes them, and the de-interleaver does the reverse operation and takes the permuted bits, puts them in the same order as the inputs to the interleaver at the transmitter, so that they're reverse operations. The purpose of the interleaver, which is a subject we will deal with later in detail, is to take the block of data and interleave the bits in such a way so that adjacent bits are not mapped to the same carrier. So that if a carrier in fact is eliminated or received with low SNR, low signal to noise ratio, and the bits associated with that carrier are in error, then those bits are not adjacent to each other when we go back to the de-interleaving process. As far as the Viterbi decoder is concerned, those bits would be in random locations, and of course the Viterbi decoder is very efficient at correcting random bits. So for forward error correcting coding to be effective in a wireless channel, wireless digital link with fading multipath channel, it is very important to include the interleaver and de-interleaver process. We will discuss the interleaver and de-interleaver in detail to show how this is accomplished, where a bursty error will not happen. In fact, if a carrier is wiped out, the actual bits that are affected would be in random locations such that the Viterbi decoder can correct them. In 802.11a, the convolutional encoder uses what you call a constraint length equal to 7, and compared to unencoded, using no coding at all, for example, if you were using BPSK, binary phase shift keying, a convolutional encoder with a Viterbi decoder with a constraint length equal to 7 actually achieves about 5.5 dB of gain. And what this translates to is that the receiver sensitivity has increased considerably. So if we use the same power or the regulatory constraints imposed by different countries, so you're limited by the power you use, then the addition of forward error correction coding with constraint k equals 7 and using convolution encoder, we can achieve about 5 to 6 dB of gain, which means that the received sensitivity is high and we can actually achieve wireless communication over a much longer range. Furthermore, with interleaving, as we pointed out, we can combat burst errors, and the fact that we are using forward error correction coding in a wireless communication link means that we can achieve robust, reliable communication and eliminate the need for retransmissions due to the reception of packets in error. If we didn't have forward error correction coding, then many packets will be received in error since we cannot correct for those errors, and it would be necessary to retransmit them, degrading the performance of the wireless communication link. So forward error correction coding is essential to any OFDM-based wireless communication system over multipath fading channels, and that is why we will spend some time discussing the convolution encoder, how it operates, and go into some detail into how the Viterbi decoder is able to decode the convolutionally encoded data and actually correct for bit errors. There are a number of references that you can refer to in order to get more insight and deeper understanding into the convolution encoder and the Viterbi decoder. One is, of course, a theory and practice of error control codes by Richard Blount, and also error control coding for data networks by Reed and Shen. We also have an excellent tutorial on the internet that you can get for free by Chip Fleming on Viterbi decoding. Chip also includes the full C implementation of a Viterbi decoder with soft D mapping. This C code, of course, removes all ambiguity in terms of understanding the operation of the Viterbi decoder. Another great reference is Bernard Sklar's Digital Communications, and he also has a detailed description of the Viterbi decoding process with examples. So in the next section, we will begin by describing the convolution encoder and the Viterbi decoder process in detail. Here we begin by discussing the convolutional encoder, which is a linear encoder, and we'll go into detail about how a convolutional encoder encodes data in order to add redundancy, such that we will be able to correct for errors introduced by the channel at the receiver. In this case, using a Viterbi decoder, which we will discuss also in detail. Over here, we show a convolutional encoder. It's a 1/2 rate encoder in the sense that for every bit that is input, we output 2 bits, so 2 code bits. The convolutional encoder is constructed using shift registers. In this case, we have a 2-bit shift register. Consider the delays D actually almost like a D flip-flop as a shift register. So as bits are input, every clock the bit is shifted into the next register and so forth. Therefore, for 2 bits, we have a total of 2 to the 2 or 4 possible states of the shift register. Usually in convolution encoders, you start out with the all 0 state, so both shift registers will contain zeros. In the case of this example of a convolutional encoder, the input is taken, we tap off the input and go into this exclusive OR, and exclusive OR the output of the final shift register with the tap off the input to obtain the output U1. And the bottom part, we tap off the 2 shift registers, exclusive OR them together, and get U2. And the way the convolution encoder works is U2 and U1 are actually put into, for example, a shift register and clocked at double the clock speed of the input information rate. So if the input bit rate is RB, the output bit rate is 2RB, or twice in this case. So this is why it's referred to as a half-rate convolution encoder. So in this case, U1 is shifted out first, and then U2. So we have U1 and U2s. For every input bit, we have 2 output bits. Exclusive OR operation is shown here, and here's the conventional symbol for the exclusive OR, and recall the truth table for the exclusive OR, in which if both inputs are 1, the output is 0. If both inputs are 0, the output is 0, and either input is 1 and the other 0, the output is a 1. It's a modulo 2 addition, actually. One other way of describing the operation of the shift registers and the taps and the exclusive OR operations is to express them in terms of a polynomial. So for example, if we have a n-bit shift register, the polynomial would be of degree n. In this case, we have a 2-bit shift register, so the maximum exponent of the polynomial is 2. So since we tap off the bit prior to going into the shift register, it would be associated with x to the power of 0, which is 1. And then, since we are not tapping off the first shift register, then the coefficient associated with x to the power of 1 is 0. But we are tapping off the second shift register location, and we have, of course, x to the power of 2. So the top polynomial is expressed as 1 plus x2. At the bottom, we can illustrate this with another polynomial. In this case, since we're not tapping off the information bit as it comes in, but we are tapping off the first element of the shift register and the second one, so we get x plus x squared. So the polynomial representation is a nice compact form for expressing the circuitry associated with the top and the bottom portions of the convolutional encoder. Without getting into too much detail here, typically with a polynomial we can express the information bits also as a polynomial, and if we multiply the information bits expressed as a polynomial by the polynomial of, for example, the top branch of the convolutional encoder, then the coefficients of the resultant polynomial are actually the coded bits U1, and similarly for the bottom polynomial. One other way of illustrating the operation of a convolutional encoder is to draw a state diagram. Here we have a 2-bit shift register, so we have a total of 2 to the power 2, or 4 states. For example, if you have a 3-bit shift register, we would have 2 to the 3 or 8 possible states. So in the state diagram representation, we draw a circle for each state and label the circle with the actual state. In this case, the 0 is the first element of the shift registers, and the next bit is the second element of the shift register, and we have the 4 possible states, of course 0, 0. If we input a 1, then we go from the 0, 0 state to the 1, 0 state on the next clock. So in this case, the 1 would be shifted in, and the 0 would be shifted into the next element, next shift register bit position, and we get a 1, 0. In the case of a 1, 0, if we input another 1, the 1 would get shifted, and the 1 would be entered into the first shift register element, and we go to state 1, 1. And if we enter, for example, a 0, then of course the 1 would get shifted out, and we get a 0 moving in. We go to the state 0, 1, and if we enter another 0, obviously we go back to state 0. In the case where we're in state 1, 1, as long as we receive 1s, we'll stay in that state. That's shown over here. So in a state diagram representation, the transition from states is indicated by this arrow here. If we get a 0, that is shown by the first element here. So we show 0, we stay in the 0 state. If we get a 1, then we move into the 1, 0 state. If we get another 1, we move into the 1, 1 state, and if we keep getting 1s, we stay in the 1, 1 state. Now, this part shows the input bit, and then the slash is followed by the output bits. So every time we transition from one state to another state based on the input, the resultant coded bits or code bits are shown here following the slash. So let's say we're starting out at the 0, 0 state. So as long as we get zeros, we stay in the 0, 0 state, and our output is also 0, 0. If we get a 1, we transition into the 1, 0 state, but before we get the 1, the shift register contains 0, 0. So we get a 1 here at the input, and we exclusive OR that with a 0, so we get a 1 for U1, and of course we have 0, 0 still in the shift register, so we get 0 for U2. So we get 1, 0, and that's shown over here. So that's the output. And of course we transition into state 1, 0. Now suppose we're in state 1, 0, and we get a 0. In the case we get a 0, then the 0 would be shifted in here, and the 1 would shift over to the right, and we'll transition to state 0, 1. So let's consider the case where we are at this state 1, 0, and we receive a 0 as an input. So if we get a 0, obviously we shift the 1 over to the right and shift the 0 in, so we go to state 0, 1. Let's take a look at what the output becomes. So initially we're at 1, 0 state. We receive a 0. We get a 0, 0 exclusive OR, so U1 is equal to 0. That's shown over here. We have a 0 here. The shift register is, of course, 1, 0, so we get the exclusive OR between a 1 and a 0, which is 1, so we get U2 is equal to 1. That's shown over here. If we receive the 1, then of course we would move, the 1 would be shifted to the right, and a 1 would be shifted in. We move into the 1, 1 state, and the output would become 1, 1, 2, because of this case we have a 1 over here. We have a 0 here, so the exclusive OR of 0 and 1 is of course 1. And in this case, the initial state was 1, 0, so the exclusive OR of that is also a 1, and we get it as an output 1, 1, as shown over here. It's a good exercise to go ahead and verify all the other labeling and on the branches for the state diagram as an exercise. Another very powerful way to show the operation of the convolutional encoder is through the Trellis diagram, which we show over here, and I'm going to explain this in detail, and it's going to be very important in terms of not only obtaining the output of a convolution encoder based on a input sequence. You will find that using a Trellis code you can actually very easily write out what the output is going to be. But the Trellis diagram is also extremely important in terms of the operation of the Viterbi decoder, which we'll describe. So the Trellis diagram is obtained first of all by labeling time from left to right as time 0, 1, 2, 3, and this is the advance of the clock. Every time we advance the clock, we're moving to the right. And from top to bottom, we basically label the states. So state 0, 0, state 0, 1, 1, 0, and 1, 1. We have 4 states, of course. And here we show that the most recent input is shown by the bit to the left. Usually in convolution encoders, we always start out at state 0, and we typically end at state 0 too. We'll talk about that later. So we begin with a node at state 0, and if we input a 0, then we go to basically the left, and if we input a 1, we go basically to the right or down, and if we get a 0, we go up. So if we're at this node at state 0, 0, and we input a 0, then we stay at state 0. So our next step, we stay at state 0. This is actually shown here. So as long as we get zeros, we just basically stay in the 0, 0 state. If we input a 1, we input a 1 here, the 1 gets shifted in, and the 0 shifts over here, we get the next state as 1, 0. So we jump from this node to state 1, 0 over here. That's when we have a 1 as an input. Now if we're at state 1, 0 and we receive a 0, again, go basically up or to the left. And the next state, if you look at your diagram here, if you are at state 1, 0 and you receive a 0, you go to state 0, 1. So here we transition to state 0, 1. So this node corresponds to state 0, 1. If we receive the 1, we go to the state 1, 1, and this is shown over here. So 1, we go this direction, 0, we go this direction. If we continue this methodology, then we can complete the trellis diagram as we consider all possible inputs, zeros and ones, and starting out at a particular state. And you'll see that after a while it starts repeating itself, which is expected. Nevertheless, it's still very important to draw out the trellis diagram. Now, one very important point I want to point out is the fact that we label each branch from the node, depending on the branch. Of course, we have two possible branches depending on whether the input was a 0 or a 1. We label each branch with the output of the convolutional encoder. So U1 and U2. So let's go over here and start out at state 0. If we receive a 1 at state 0, recall that our next state was state 1, 0. Again, over here, 0, we receive a 1, we go to 1, 0. But look what the output. The output during that transition, U1 and U2, is 1, 0. So we label that over here on this branch. So each branch you will see a label, and that's the output of the convolutional encoder. Let's take a look at this case where at state 1, 0. So if we're at state 1, 0, receive a 0, we go to state 0, 1, and the output is 0, 1. Let's take a look at that. So if we're at 1, 0, we receive a 0, we go to state 0, 1, and the output is 0, 1, and that's shown here on the label on the branch. If we receive the 1, the output is a 1, 1, and we show that on the branch. As an exercise, you might want to actually complete this and verify the fact that all these labels are correct on the branches as we transition between states, depending on whether we get a 1 or a 0. Now, to highlight the value of the trellis diagram, let's take a look at the next diagram. Here we're showing the trellis diagram, the same one we showed before, right over here. And we have an input stream. So this is very important. We have an input stream, which is we're receiving a 1 followed by another 1 followed by 0, 0, 1, 0, 1, 0, 0. These are the inputs. What we're interested in is what is the output stream. For example, the number of bits, let's see, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, for example. For 9 input stream bits, we obtain, of course, 2 times 9 or 18 output bits, and these are shown here. So for every bit we get, we obtain 2 output bits from the convolution encoder. So let's go back to the trellis diagram, and you'll see how easy it is to trace through the trellis diagram and then read off the path what the output bit stream is. So we always start out at state 0. We receive a 1 input, so obviously we go down. And then we get another 1, so we go here. We get a 0 here, so we go over here. Just follow the branch. We get another 0, we go over here. And following that 0, we get a 1, and just proceed down. Here we get a 0, we go down, we get a 1, we go over here. And then followed by 2 zeros, and we go back to the all 0 state. So it's very easy to trace out the path through the trellis diagram due to a input sequence. Now this particular input sequence, recall that we always start out at state 0, 0, and purposely this input sequence we have at the end 2 zeros, and that corresponds to the length of the shift register, which was a 2-bit shift register, and this way we always flush out the shift register and always return to state 0. Let's see how easy it is to read out what the output bit stream is. So just take this branch here and look at the label on the branch, and that's your output. So you just output 1, 0. Take a look at this branch, look at its label, it's 1, 1, just output 1, 1. Look at this branch, look at its label, it's 1, 0. Look at this branch, its label is 1, 1, and so forth. So just read off the labels off the branches and you have the output stream. It's that simple. So we've shown that through the trellis diagram it's very easy to come up with a path given the input, what path is taken through the trellis diagram, and then by reading off the labels on the branches, we can actually obtain the output stream given an input stream. Going back to the convolutional encoder, there's a few more points I would like to mention about the properties of a convolutional encoder. First of all, a convolutional encoder is a linear encoder, and unlike a block encoder, it has memory. Block encoders are usually memoryless. That is, the code words only depend on the present information bit. They do not depend on the previous information bits. So for example, if you collect a number of information bits and use a block code and add, for example, more redundant bits to it, it only depends on that collection of information bits, and it doesn't depend on the previous information bits. But in the case of a convolutional encoder, the output codes depend on the previous values of the information bits, and that's due to the operation of the linear sequential circuit here, the shift register with the operations as we've shown. So every bit actually depends on the previous information bits, and in fact it is this fact that the convolutional encoder introduces redundancy that depends on previous information bits that results in its powerful error correction and error correction coding capabilities. Of course, a full analysis of convolutional encoders is beyond the scope of this presentation, but we will do our best to highlight all the important issues. One other important thing we want to mention is the fact that each particular convolutional encoder has associated with it a parameter called the constraint length K, and the constraint length is equal to the size of the shift register. In this case, the shift register is 2 bits. So we have 2 bits, 2 memories for the shift register. So M equals 2, and the constraint length K equals M plus 1. So you basically, to get the constraint length, you take the size of the shift register to the number of memory elements and add 1 to it. So for example, for 802.11a, as we will show, the constraint length K equals 7. So the shift register is 6 bits, and you would have, in fact, 2 to the 6 or 64 states, possible states for the convolution encoder used in 802.11a. Going back to the trellis diagram for the convolutional encoder that was shown before, we noticed that if we did put in an input stream, we can easily go through and show the path through the trellis diagram, and then from the path actually write out the output sequence of the convolutional encoder. Now, as these bits are transmitted, they go through a channel, and assuming, for example, additive white noise channel, then of course you encounter errors. Errors are made so that the received code is different than the transmitted code, and you have bit errors in the received code. And of course, using convolutional encoders, typically we use a Viterbi decoder to decode the convolutional encoder bit stream. The Viterbi decoder is a maximum likelihood decoder, which we'll get into, and has a great property in correcting random bit errors, not bursty errors. So typically in an additive white noise channel, the bits would be randomly, errors are made randomly among the bits, and the Viterbi decoder would correct those random bits. It is not good for bursty errors in which adjacent bits, many adjacent bits are in error, and which typically happens in a multipath channel when, for example, one carrier runs into a deep fade. But there's another error correcting method called Reed-Solomon, which is a linear block code, and that corrects bursty errors and usually can be used in combination with convolutional encoder and a Viterbi decoder as the inner forward error correcting code, and the Reed-Solomon would be used as the outer. And sometimes when a Viterbi decoder decodes things, it'll give if it doesn't correct it correctly, it'll give a burst of errors. And of course, the Reed-Solomon is good at correcting bursty errors. It's actually used in, for example, CD-ROMs. But that's we'll get into that when we talk about 802.16a. So for a particular input bit stream, we traverse a path through the Trellis diagram unique to that particular input stream. And what happens is when you have errors, this path will not be traversed. And one way to correct for errors, actually one way to decode, given that you receive a stream, is to look at the distance between all the possible paths through the Trellis diagram and that particular received sequence, and find the path with the minimum distance, and then assume that that was the actual output stream that was sent, and consequently you can decode the input stream associated with that output stream, decoded output stream. However, as you can see, when the constraint length is increased, for example, when it's equal to 7, then you'll have 64 possible states, and the number of paths grows exponentially, and this is not a viable way to decode. More efficient ways to decode have been developed. In particular, we'll talk about the Viterbi decoding algorithm, which is a maximum likelihood decoding, and is very efficient and is optimum. Let's review some of the issues regarding error correction, and we want to also introduce Hamming distance. Although many people are familiar with this material, it's good to review this. Let's suppose you have a code word C1 shown here, and you have another code word C2 shown here, and one way to characterize the distance between these two code words is to actually do a modulo 2 summation of the codes bit by bit, which we've done over here. So C1 plus C2, again, this is modulo 2 addition, so every bit is exclusive OR with each other. And if we do that, we got the exclusive OR 1 1, you get 0, 0 0, you get 0, 1 1, you get 0 again, 1 0. So here we have a difference between the two code words. At this bit position you get a 1 1 1 for the differences here, no difference here, so that's 0 0. You have a difference here, so you 1 0. So effectively C1 plus C2 gives you another code word, and let's define the weight as the number of ones within that code word. So the weight here would be 4. It turns out that that weight is exactly equal to the Hamming distance between the two code words. So the Hamming distance basically measures the number of bit errors, so to speak, between the two code words, if we're talking about errors, or just the distance between two code words. If we consider linear block codes, and in the case shown over here we have n code words that form a subset, then if you measure the distance between codes pairwise and form a set of all the distances between the codes, and from that set select the one with a minimum distance, then that's the minimum distance of the code words that form the subset. Now it turns out that for linear block codes, the sum of two codes is also a code within the subset. So C2 plus C3 will also be a code within the subset. We exploit this fact as follows. If we take a code, a particular code from among the code words, and add that code word or subtract it from every other code word, then we form code words that are also in the subspace of code words. But we also have the all zero code word. So to find the minimum distance for a subspace of code words, it is sufficient to find the distance between all code words and the all zero code word, and select the minimum distance from that computation. So the procedure is to find the distance between all code words and the all zero code word, and from among them pick the one with the minimum distance. That's the minimum distance of that subset of code words. We will exploit this property for convolutional encoders next. This is pretty convenient for convolutional encoders because we have the all zero state over here. So to find the minimum distance capability of convolutional encoders, and of course decoders, the various algorithms used to decode convolutional encoders, the minimum distance can be analyzed in terms of the distance between all particular code words, all possible code words, and the all zero code word. Let's take a look at error correction for a minute here. Let's take the case where we have a code word shown over here, and we have another code word shown over here, and these are valid code words that are associated with the information that is transmitted. That is, the information transformed into these code words, and the code words are then transmitted to the receiver. The receiver then receives these code words, but since it goes through a noisy channel, the code word gets corrupted by noise. Errors are actually made in certain bit positions, and instead of receiving the code word, we may receive these particular vectors shown over here, these particular numbers shown over here within the space of all the codes. We look at the possible received codes due to errors, and we look at the valid codes. Then if the distance between these two codes, between the valid codes, is large, then we can possibly decode the received codes in such a way as to actually correct them. And this is shown over here. So if we draw a boundary at the middle called the decision boundary, then if the received codes are to the left of that boundary, then we can assume that, and this is a maximum likelihood type decoder, then we can assume that this code was sent. And if, of course, it falls on the right-hand side, we can assume that this code was sent. So we're actually decoding by calculating the distance between the received code and the valid codes, and picking the code with a minimum distance, and then assuming that that was the code that was actually sent. This is, in fact, is a maximum likelihood decoding procedure. Now notice that if the distance is large, then we have a capability to actually correct errors. So for example, here we have a Hamming distance of say 1, and here we have a Hamming distance of 2 between the possible received erroneous codes and the actual sent code. In this case, we're able to, since this code would be closer to the code that was sent, then we would make the decision that this code was sent. And although we had 2 bits in error, we were able to correct the received code. So the error correcting capabilities of a particular coding method depends on the minimum distance. So the minimum distance is 1, 2, 3, 4, 5. So the error correction capability here is actually 2 bits. So with a dmin equals to 5, we can actually correct for 2 bits in error. So this particular scenario would give us a 2-bit error correcting capability. So we have basically shown the fact that for a particular coding method, the performance or error correction capability of that particular code depends on dmin, the minimum distance. And what happens with the convolutional encoder is that since the coded bits depend on the previous bits and a particular way that the convolution encoder works, that is, it depends on memory and all the previous bits. And given the Trellis diagram that you see over here, in fact, convolution encoders can, by increasing the constraint length, and that is the dependency of the existing bits on previous bits, you can actually achieve a larger and larger minimum distance. And of course, the power of a error correction capability of a particular encoding method, error correction code, depends on the dmin. So increasing the constraint length increases dmin, and therefore the error correction capability. We'll show some simulations that verify that point later on. We will now discuss Viterbi decoding, which is a maximum likelihood decoder for the convolutional encoder. It is optimum. It is an iterative procedure and simplifies quite a bit the decoding of the convolutional encoder. And for this reason, it is used quite a bit in industry. In fact, it is one of the most predominant decoding algorithms used. Instead of going through the whole derivation of the Viterbi decoder, what we'll do here is actually illustrate it step by step in decoding a data stream that's received with bit errors. Here we show the Trellis diagram again, and this is of course time. As we clock, every clock step we show 1, 2, 3, 4, advancing in time. And of course we have the states. We have received a stream, which is 1001111, etc. And this stream is, of course, a result of the convolutional encoding that we showed before. We don't know what the input sequence was to produce this stream, and all we know that it may have errors because it has gone through a noisy channel. The way the Viterbi decoder works is, given that we always start at the all zero state, we assume that we either received a 0 or a 1. So we move from state 0 in the case that we received a 1 to state 1, 0, just going through the Trellis diagram. Straightforward. Of course, if that was the case, then the output of the convolution encoder would have been 1, 0. We compare that with the output, the received stream, what we receive, which is 1, 0. And we compute the Hamming distance between these two, and it's of course equal to 0 since they match. So we set d equals 0, and this is of course the branch metric for this branch right here. On the assumption that a 0 is sent, then we go from state 0 to state 0 again, and the output would be 0, 0. We compare that with the received sequence 1, 0, and we find that we have a difference in one position, so d equals to 1. That's the Hamming distance for this branch. At every node, then we have the accumulated branch metric mu, which in this case is 0, and in this case is equal to 1, since d is equal to 1. Now at this node, we either can receive a 0 or a 1. If we go with a 1, then we go from this state to the state 1, 1, from 1, 0. And we output a code word of 1, 1. Compare that with the actual code word that we received 0, 1, and we find a distance, Hamming distance of 1, so we write d equals 1, and of course we go to this state. For an input of 0, we move to state 0, 1. The output is a 0, 1, and if we compare this with the receive sequence 0, 1, the Hamming distance is equal to 0. We label that, and we move on to this node. If we continue at this node, if we get a, for example, 0, we go down here, and if we get a 1, we go back to the state 1, 0. Consider this situation here. So for the 0, we go back to state 0, and we output a 1, 1. Compare that with the receive sequence 1, 1. The Hamming distance is 0, so we label that. As we start going from this path, by the way, we have a mistake here on step from 1 to 2. D should be equal to 1. But if we go along this path, you will notice that the Hamming distance, and we indicate that step 1 to 2 should be 1, but from step 2 to 3, the Hamming distance is equal to 2 because we compare 0, 0 to 1, 1, and the accumulated distance is equal to 4 for this path. If we look at the other path, the accumulated metric is equal to 0. So this is where Viterbi decoding comes in. We have basically arrived at this node through two separate paths, and for each path we have an accumulated metric. And here's where we select the surviving path based on the path which had the minimum metric, the minimum accumulated metric length, which in this case was 0, and for this path was equal to 4, so we don't need this path and we eliminate it. So this path is eliminated, we don't need it anymore, we throw it away, and this is what you call the survivor path. So we keep going. At this point, for a 0 input, we move on to step number 4, and the output, of course, is 0, 0, and we compare that with the received output. The Hamming distance is equal to 2. Now, coming to this particular node, we also have another path shown here, and if we look at the accumulated metrics for this path, we have d equals 0, d equals 1, d equals 1, d equals 0, so the accumulated metric is equal to mu equals to 2 versus the accumulated metric from this path, which was equal to 2. And basically you can eliminate one of these paths and just keep one of them, even if the metrics were equal. You basically can do a toss-up and select a particular path, one particular path, even though the metrics were equal. You would still correctly decode in Viterbi decoding. Let's take a look at the situation of this node here. So to reach this node, we have one path through this path here, and we have another path through here. And again, let's take a look at the accumulated branch metric so we can figure out which path is the surviving path. Going through this path, we have d equals 2, d equals 1, so we got 3, 4, so the mu is equal to 4. And going through this path, we have d equals 0, 0, 0, 1 over here, so the accumulated metric is equal to 1. So this path has an accumulated metric equal to 1. This path has an accumulated metric equal to 4, so the surviving path is this path, and we eliminate this path. So we continue this process going forward until you're left with a few remaining surviving paths. All right, so for example, we have a number of paths that I'm showing here. For example, with an accumulated metric of mu equals to 1. You have another surviving path over here with accumulated metric equals to 2, and a surviving path here with an accumulated metric equal to 3. At some point, of course, you're going to call it quits, and you're going to look at the various paths and select the path with the minimum metric, and that would be the path that you would assume was transmitted. And of course, it helps that as we know, the shift register size, the number of memory elements in the shift register was, for example, 2. Then you use 2 0, 0 flush bits to move the state back to the 0 state, basically flush it. So this seems to be the correct path right over here. So going to the next diagram, we see that this is the path that we've selected with the least accumulated metric and eliminated all the other paths. Now, if this is the path that was taken, we can actually read out what the transmitted code words were. So basically here the output is 1, 0. Let's write that down. So the decoded stream, we have 1, 0. We have 0, 1. We have, for here, this path here, again 0, 1. This path here, we've got, of course, 1, 1 going from here, then 0, 0, 1, 1, 0, 0, and then going from here to here, we have 1, 0. Going from here, we have 1, 1. And of course, going from here, we have 0. So this is the actual decoded stream. At the top, I'm showing the received stream that we used in order to arrive at the decoded stream. And we'll notice that we have 1 bit error at this position. Knowing the path through the trellis, we can easily write down what the actual input to the convolutional encoder was, what the information bits were. So in this case, since we're taking a right turn here, so that's just 1, 0, 1, 1, 1, 0, 0, 0. And that's what we write down right over here. So it's very easy to just write down what the decoded message was. So we've shown how the Viterbi decoder can actually decode a received stream that has bit errors and actually correct the errors, and very conveniently we can write down the actual decoded message, which was the input to the convolutional encoder. By the way, the path metric, the accumulated path metric, equals actually the number of bit errors. So here we have 1 bit error, and in fact mu is equal to 1. So that's another property of the Viterbi decoder. A few points on complexity. So the complexity obviously grows exponentially with the number of states. So as we increase the constraint size, the constraint length, then the size of the Viterbi decoder, the Trellis diagram, grows exponentially. And in practice, when you implement a Viterbi decoder, you have to store the whole Trellis diagram in memory. So the memory size you'd have to have a 64. For example, if you have a constraint length of 7, then you would have 2 to the 6 number of states. So imagine a matrix with 64 rows, and the number of columns is associated with the constraint length. Now, the number of columns that you store is typically 5 times the constraint size. This diagram shows a traceback depth of up to 8 clock cycles. The traceback depth is typically a multiple of the constraint length, and if depending on the amount of errors that you need to correct and severity of the problem, traceback depths of 5 times the constraint length or higher are required, say 7 times. In this case, we're using, if our constraint is equal to 3, so 5 times 3 would be 15, but of course we achieve our goal by 8. It all depends on the situation. If you have puncturing, then you need a larger traceback depth, much larger than, say, 5 times. You need to basically store these paths so that once you've figured out which path is a surviving path, you can go back and also from that from the trellis path actually get the actual message that was sent. So without getting into too much detail, there are a lot of issues involved with implementing a Viterbi decoder, and there's also these add, compare, select butterflies that we've shown here. Basically, you add the various paths and select the one with the minimum, and of course that's a whole different topic, and many papers are available in the literature on the implementation of Viterbi decoders. This diagram is very interesting, and the source for this diagram, of course, is the great tutorial by Chip Fleming, which is available on the internet. And based on his tutorial, he actually implements a soft demapping Viterbi decoder and soft bit demapping, and he actually has run a number of simulations for various constraint lengths and compared the performance for the various constraint lengths. So let's discuss this diagram. First of all, you can think of this diagram as we are plotting the bit error rate versus the EB/N0, which is related to the signal to noise ratio. EB is the energy per bit, and N0 is the one-sided noise power spectral density, typically in watts per hertz. And typically bit error rate curves are plotted against EB/N0, which can be related directly to signal to noise ratio. We'll discuss this in a future topic. The first curve that's shown over here is the case where you do not have, and this is for example, BPSK type simulation coding, where you have just +1, -1 or binary encoding. This curve here shows the probability of error versus the EB/N0, and this matches exactly the Q function. And so the theoretical curve is shown, and also the simulation, and you'll notice the simulation matches the theoretical perfectly in the simulations. This point is very important, and we'll get to that. This is the point where the bit error rate is 10 to the -6, and it happens to be at the EB/N0 equals to 10.5 dB. All right. So what if we use forward error correction coding, and how does that improve our performance? So in this case, we use a constraint k equals 3, which is what we've been discussing. So you have m equals 2 as the size of the shift register, 2 memory elements. And you get a dramatic improvement in the bit error rate performance versus no forward error correction. So if you look at here, for example, at an error rate of 10 to the -5, we're seeing a more than about 3.5 dB improvement over the not using forward error correction. And this is huge because 3 dB translates to using half the transmit power, for example, to achieve this quality here. So to achieve 10 to the -5 using forward error correction with a Viterbi decoder, then I can cut the transmit power in half, for example. There are many trade-offs involved, but 3 dB, typically think of it in terms of requiring half the transmit power to achieve the same quality. Now, as we increase the constraint size, for example, this curve here where k equals 5, the green curve, when k equals 5, we see another about almost a dB improvement. And as we increase the constraint to 7, which is what's used in 802.11a, we see another dB improvement over k equals 5. And of course, this comes at a price because, as we mentioned, the higher the constraint length, the more complex the Viterbi decoding algorithm and the hardware requirements in order to implement it at high speeds. but the improvement is again huge, even compared to k equals 5. For constraint length equals to 9, of course we get another about half a dB improvement over k equals 7, and sometimes that's worth it if you're willing to pay the price in hardware complexity and extra power consumption and so forth in the silicon. So as we increase the constraint length, we get better and better performance, and this curve is a great reference in order to go back and see if you're doing any design what appropriate constraint length you would like to use in order to meet your objectives for your communication link. So far we've been talking about hard decisions in our Viterbi decoding. So when we discussed the example with a Viterbi decoder, we mentioned using Hamming distances, and Hamming distances imply the use of hard decisions. In the case of hard decisions, for example, if we receive the constellation shown here for a QPSK system, we receive a noisy constellation point. So these are the actual received constellation points. The ideal constellation point, of course, is at the middle here. In the case of hard decisions, we would take, even though we receive these various values here, these various vectors, so to speak, we would actually decode this as, for example, 0, 0. We'd make a hard decision that we decoded 0, 0, and the Viterbi decoder would then use Hamming distances and so forth as we illustrated before. However, it is important to note that the received information, that these vectors that we actually receive have information associated with them that we're throwing away when we make a hard decision. So rather than use Hamming distances, what we do is we actually take the received vector as is, and we actually use the Euclidean distance. So we actually measure the distance directly in terms of the difference between the vector lengths. This, of course, would require floating point operations and a huge amount of complexity in order to compute all the metrics. Because again, in this case, we're using floating point and we're using the Euclidean distances. One way to get around that is to actually quantize the received information, the received vectors. And here we show a 3-bit quantizer. And if we use these various quantizers, then we're making soft decisions, and basically using the quantizers we can avoid a lot of the floating point operations and minimize the hardware requirements. Now it turns out that using soft decision demapping and Viterbi decoding gives you a substantial gain in performance. Roughly, for example, from going to 3 bits, you can gain up to 3 dB, 2 to 3 dB improvement. And if you go up to 5 bits, maybe get more, another dB or half a dB improvement. Let's take a look at that. So soft decision Viterbi decoding has about 3 dB gain over hard decision. This is based on all the references and, of course, many simulations. After you increase the number of bits for quantizing the received constellation points, most of the gain is achieved around at about 5 bits. Going beyond 5 bits doesn't give you any more gain compared to going to a full floating point implementation. So about 3 to 5 bits is what you're aiming for in terms of soft decision demapping. In some references, which I'll point out, they actually show that for 16 QAM and 64 QAM, you can achieve 5 to 6 dB improvement over hard decision. And let me give you that reference because it is very relevant to 802.11a, even though it is for Hyperland 2. This is a great paper. It's done at HP Laboratories, simplified soft output demapper for binary interleaved COFDM with application to Hyperland 2. So basically I'll refer you to this paper in order to get the details in terms of using soft demapper with 16 and 64 QAM. They also go through a number of simplifications which reduce the hardware considerably, but at almost no cost in terms of performance. Here we show the convolutional encoder used in 802.11a. And as you can see, the convolutional encoder has a constraint length equal to 7, and therefore it has 6 bits used for the shift register. We also show the generator polynomial for the top half, which is shown here. The coefficients are shown in terms of octal, and we've also written out the polynomial corresponding to the generator polynomial shown in octal over here. And you might want to verify that. Also, for the lower branch, we've expanded the polynomial for the generator polynomial. The first bit that is output is A, then B, of course, is a half-rate coder. Constraint length is equal to 7, and we showed that the constraint length equal to 7, you achieve quite a bit of improvement over not using any forward error correction. And this encoder also implies a hardware complexity such that you need to store 64 states. The traceback depth typically used in 802.11a may be anywhere from 60 to, in size from 60 to 90, and you may need a larger traceback depth if when you're using puncturing. So if you are using puncturing, you need a larger traceback depth.